So, hello everyone, welcome to today's Quantum Space-Time seminar. We are very happy to have Apratim Kaviraj from DESY, who is going to tell us about some functional aspects of conformal bootstrap. Over to you, Apratim.
So thank you, and thanks to Avijit, Pushkal, and everyone at the IFAR to give me this wonderful opportunity to present this seminar here. And so this is my first virtual seminar in TIFR. So it's a bit more formal than the previous seminars I have given. So, but please don't let that stop you from asking the questions. So I will begin with some motivation and a brief introduction to what I'll talk about, and then I will slowly move on to the more formal aspects of the work. So let me just begin with saying that, well, conformal field theories are important for all theoretical physicists, as we know. And so my talk today will be on the conformal bootstrap approach, which is a nice tool for finding conformal field theories, and by relying only on fundamental axioms and symmetries. The first formulation of the conformal bootstrap dates back to 30 years, 40 years from now, by the work of Polyakov and also by Grillo and Gatto. And then it was revived 30 years later as a very efficient numerical approach to obtain conformal CFT data. By that I mean critical exponents, and also as a nice alternative to existing methods like Monte Carlo. And till date, the conformal bootstrap has proven to be even more useful than just constraining conformal field theories. It ties in AdS CFT, scattering amplitudes, and even constraining the space of general quantum field theories. So an important goal for us bootstrappers is to find a systematic formulation that gives us a good analytic control of the CFT search and not just do blind numerics. And so I will discuss some of these ideas which really helps in with this motivation. And these ideas are broadly, I call them broadly as analytic functional bootstrap, and this is also related to many of the modern ideas in the CFT literature. And finally, I'll also show some exciting recent results for some interesting CFTs. All right, so this is a rough plan of my talk. So I'll begin with some very basics of conformal field theories, some very basics of bootstrap. And well, most of these things are, I'm sure this audience already is well aware of, but it will still help me to introduce the notations which I'm going to use throughout the talk. And then in part 2, I will move on to the background necessary for the subject, which will include what is called the Polyakov bootstrap, dispersion relation, a CFT dispersion relation, and the so-called analytic functionals. Then I will move on to the newer things, which are some nice generalizations of these ideas. And finally, if time permits, I will show some great applications and new results of these things. All right, so finally, so let me begin with saying that, okay, that's, if you have a CFT, then the 2-point and 3-point functions of the conformal field theories are, as you all know very well, they're totally determined. So 2-point functions, they have this form of us. I'm talking about scalar operators, and the 3-point functions of 3 CFT scalars have this form. And from 4 and higher point functions, a correlation function is determined only up till 2 cross ratios, which look like the following. And so this Z and Z bar cross ratios are going to appear throughout my talk. Give me a second. Okay, so for any, so what is important to evaluate 4-point function is what is known as the OPE, or the operator product expansion, where we take, if you have two products of operators, let's say two scalars, and so in CFT permits us to expand it as a sum over all types of primaries and their descendants. And this OPE could be inserted in a 4-point function to obtain what is called conformal block. So I just inserted this OPE into a sum over into 4-point function, and I got a sum over conformal blocks that depends on the dimension of the primary operator and their spins. So please stop me if you have any elementary question about all these things. So what does a conformal block look like? The conformal block in 1D has this following form. It's a simple hypergeometric function. In even dimensions, conformal blocks have a factorized form in terms of the 1D conformal blocks. For instance, in 2D, the conformal block has this factor look like the following. They look like the following in terms of this G delta minus L and G delta plus L are 1D blocks. And so this is what happens for even dimensions. For generic dimension, the blocks can be obtained through recursion relations and by solving the conformal Casimir equation. All right, so now let me show you an example of a CFT, which will be very important in this talk. It's a very simple CFT. It's called the generalized free theory, or the theory of generalized free bosons. And it is defined by free quantum field theory in AdS, free scalar quantum field theory, which has the following action. And from weak contraction, you can determine their 4-point function of 4 phi's, which has the following form. So if you take this 4-point function and you decompose it into conformal blocks, you get what you can easily identify is that the operator content, the operator spectrum of this 4-point function contains the identity, which is dimension 0 operator, and the double trace operators, which have this following form. Right. So now, how do you? So moving on to some elementary things of the conformal bootstrap. So far, this was just some basics of CFT. So here, take a 4-point function of scalars again, and let's expand it in conformal blocks. So last time, what I did was I expanded the first two and the third and fourth operator in the OPE, but there is also another way of expanding the 4-point function. It is if you can use the OPE in the second and third and the first and fourth operator separately. So this is nothing but using the associativity of the operator product expansion. You get a different expansion, which is called the T-channel expansion, while the previous one I would call the S-channel expansion, and these two should be equal. In order to use this in an efficient way, I write the bootstrap equation like as follows. I write what is called a bootstrap vector, which is a difference of the conformal blocks in the S channel and the conformal blocks in the T channel. And right now I'm considering 4-point function of identical scalars for convenience. So yeah, in terms of this, the bootstrap equation gets a very simple form. It just becomes a sum over these bootstrap vectors equal to 0.
Apratim, sure. One question. In this equation, there should be a factor which is not.
Yeah, sure. Indeed. I'm being a bit.
How are you organizing it?
So in principle, there should be some z. You are talking about some powers of z to the power 2 delta phi and so on. Yeah. Sure. I'm just being very schematic. So it should be z to the power 2 delta phi and 1 minus z to the power 2 delta phi. something like that, so now let's, how do you make use of that equation? So what you do is you take the bootstrap equation in terms of the bootstrap vectors that I just showed, and you Taylor expand it. So each component of the Taylor expansion of this guy is a different equation. That's how it's treated. And in numerical applications of bootstrap, and evaluate all these derivatives at a certain point, and that point is chosen to be half, so z and z bar to be half and half for convenience, and also because it's nicely convergent in around close to this point. So typically in numerical studies, what one does is we assume unitarity, which means that the OP coefficient should be bigger than 0. OP coefficients are bigger than 0 because it's a sum over square. It's a square of the 3-point function coefficient. So it should. So we consider this to be bigger than 0, and then we have to also impose a gap in the spectrum, which means that so it means that the lowest operator is identity, and then the next operator is not close to 0. It has some finite dimension, and then we also impose any other symmetry that we may be interested in. So with this, we can go ahead and see if a certain conformal, we can constrain the space of conformal dimensions. This is how numerical bootstrap typically works. So these are some.
Can you explain why C is positive?
So C is positive because it's the OP coefficient that appears in the 4-point function. So let me go back. So C here, so the C that I talked about is basically a product of these two guys, which came from using the OP 2 times. And for identical scalars, it becomes a square. And if
for only identical scalars, it will be square, right? In general.
Sure. In general, no, not really. Yeah.
So how is it positive in general?
It's not positive in general. Currently I'm talking about identical scalars only. But if you have not identical scalars, then you have to do some tricks and arrange the bootstrap equations in a certain way that that you can impose a sector of that you can partially impose positivity. These tricks are usually implemented in what is called a semi-definite programming for the numerical bootstrap, and they become important when you have non-identical scalars. So you have to arrange the bootstrap the cross symmetry equations for non-identical scalars in a clever way to still use some form of positivity. But yeah, for that, what I'm talking about, yeah. So some of the nice results that people have obtained in the numerical bootstrap are as follows. For example, so what one can do is one can take some value of the external dimension and try to maximize the gap, try to maximize the dimension of what is it, and ask the question, what is the maximum dimension of the first or the lowest operator, which is not identity, that is allowed in the spectrum. And such plots typically look like the following. And so for instance, in the case of the 3D, so for instance, if for the 3 dimension, what one finds is one finds a plot like the following, where the external dimension is called delta sigma, and then the first operator in the spectrum is called the delta epsilon, and the max and for each of these points, this represents the the maximum gap allowed. And one finds that that there's a kink in this plot, and this kink is found to be close to 3D the Ising model, which is often believed that it is the position of the 3D Ising gap. In 1D, the picture is a little bit different. If one does the same thing, if one tries to maximize the gap for each value of delta phi, or I just call it delta psi here, one finds the spectrum of the generalized free fields. So for each delta phi, the value that these points represent is the first operator that you should get in the spectrum of generalized free theory. So what it means is the saturation of bounds.
Why does this first non-identical operator is so important?
Why is that? So the thing is, so it's important in the sense that I'm imposing a gap, and I'm trying to find some solution that close to that. I'm trying to find I'm trying to find. I'm asking the question if there is any interesting CFT at the maximum gap. So when I impose the gap, I do not automatically know that the CFT will be interesting. But it turns out that indeed, when the gap becomes important, when the bound is saturated, for some reason I am finding interesting solution. I don't have a good reason why that happens, but it's an observation. And the expectation is indeed this, for some reason, interesting CFTs should lie only at the bounds, and what lies below this bound may or may not be interesting. We cannot really say right now. So but main question that I want to address is, can we understand the optimal bounds better, at least to which we have certain understanding of. So yeah, so that's the. So I don't know if that answered your question, but yeah. So anyway, so the question, so the point that I want to make is that indeed optimal solutions that saturate the bounds are important, and let's try to understand how that happens, and the optimal solutions a bit better. Why am I talking about all these things? Is because, well, I just showed you optimal solutions are interesting on their own. As for example, the generalized free field represents scalars and free scalars and fermions in AdS2. And also, if someone gives me, if for somehow you give me an optimal solution, you can try to flow to some nearby other interesting solutions too. So that way, bootstrapping from one optimal solution to some nearby other optimal solution is easier, and you also find other interesting solutions that way.
Apratim, can I ask some general question about the generalized free fields?
Sure.
So the correlation function, as you said, can be calculated from Wick contraction, and it corresponds to this dual free theory in the bulk. Is there a way to understand that if the theory is dual, the dual theory is free, it obeys certain equation, right? The correlation functions of this theory should obey certain equations. If I'm inserting those operators, del square plus m square equal to 0, right, locally, then can I understand that correlation function also somehow as obeying certain differential equation?
So you want to, if you're asking the question, if you give me the exact spectrum of the GFF, does that automatically,
I'm just saying, is there a set of differential equations for which this correlation function is the solution?
I mean, you can just give me a moment.
It's a stupid question.
So yeah, I'm not automatically sure if such a. So
Okay.
For instance, if you can imagine a Witten diagram, and typically if you insert the Casimir equation to an exchange Witten diagram, and then the Casimir equation reduces it to a contact diagram. There are equations like that for a single exchange, if you want to imagine like that, but I don't see any equation that should hold for the whole 4-point function itself.
Abhijit, is this the same as the question of whether the operators have a null state?
Yeah, the operators don't have a null state, right? But the field phi did. So I was wondering if there is a signature of that null condition.
Where the bulk field phi was free.
Yeah.
That was what you were wondering.
Yeah, if there is a signature in the correlation function of that fact.
Right. Typically, just on the boundary, equations of motion happen when the field obeys a null state, right? Is there a...
Yeah, exactly. So when that becomes free on the boundary, you will get it.
Right. Is there a situation, some situation where the boundary does not have, the operator does not have a null state, but there is an equation of motion for the correlation function that you know of?
I don't know.
Okay, thanks.
Yeah, but I was just expecting some consequence of the
I understand. Yeah,
consequence of the bulk freeness.
No, I understand your question. I was just
okay.
Yeah.
So if I may move on.
Yeah, please go ahead.
Thanks for this discussion, by the way. So I'm coming back to this case of the optimal solutions. So these are some of the reasons why you should care about optimal solutions. And let me now ask the question. So optimal solutions were obtained from numerical bootstrap by inserting a large number of derivatives. So you can never really get to the optimal solutions precisely. You just get an approximation. Can we obtain optimal solutions directly? So let me ask this question now. Is there a way to obtain the CFT that saturates the bound directly?
Sorry, Apratim, can you define the optimal functional a little bit precisely?
The
optimal solution.
Optimal solution is the CFT for let's say for any delta phi. The CFT that saturates the bound is the optimal CFT solution. That's my definition.
CFT that saturates. So you first of all have to find a bound.
Yeah. And
then you have to find a CFT.
That is correct.
Okay. That is correct.
Currently it's not a very well-defined CFT because it just have one operator, but the hope is that this does follow from some CFT.
Okay.
So can we obtain this solution directly? And the answer is that it is, and it actually follows from Polyakov's original bootstrap idea. So let's have a quick review of what Polyakov's original bootstrap is. So yeah, so it's called the Polyakov bootstrap, and it's you may have heard its modern iteration in some talks of one of these people. And so what it says is that let's take a 4-point function of scalars, and let's claim that it allows an expansion in exchange Witten diagrams with scalar external legs as follows. And also you can keep a contact Witten diagram with a 4-point interaction vertex in AdS. So let's make a weird claim like that. The nice thing about this is that it's an expansion and manifestly crossing symmetric combination of Witten diagrams. So this combination is automatically crossing symmetry. Witten diagrams, on the other hand, decompose into double trace blocks. This is some property of Witten diagrams that is well known. If you didn't know about it, just believe me for the moment. And so it decomposes. So Witten diagrams decompose into this kind of double trace blocks. And however, the correlation function is not supposed to have, in general, such blocks, but it should be equal to a usual conformal block description, like the following. So how does it? So what happens? So how does?
Sorry, Apratim.
Yeah.
This Witten diagram also has a block for the exchange guy?
It does. I'm just so this is what I am. So what we're saying is the following: is that the Witten diagram description has an exchange diagram, and this exchange block comes from the S-channel Witten diagram. The other Witten diagrams that I've drawn here, if you decompose them in S-channel blocks, they do not have such an S-channel conformal block. So it's only this guy that gives you an S-channel block of a dimension that is here. So the same operator that gets exchanged here appears in this block, and everything else follows from all this type of these Witten diagrams. And please realize that it's the first guy. It's already what we should expect as the usual conformal block decomposition of the 4-point function, and everything else needs to go. So this whole part we should set to 0 term by term, and this gives us the Polyakov bootstrap equations. It says that the sum over each coefficient of these guys, A's and B's, sum over them are 0. So this was a quick review of the Polyakov bootstrap tool, and these bootstrap conditions are trivially satisfied by the 1D generalized free field CFT, which is the optimal solution that I was talking about. And it's extremely efficient in general dimension for analytic computations, which I'm not really going to talk about much in this talk. And however, this formulation lacks a very rigorous proof. It didn't have a very nice understanding for a long time. So can we establish these conditions from usual crossing symmetry? So if you gave me the usual crossing, the bootstrap equation, which I have talked before, can we connect it to this conformal? How do you connect it to this Polyakov bootstrap approach? So I will now describe a little bit of the proof of this, but any questions so far?
Can you go to the last slide where this L and L prime was there?
Sure.
Okay, so L is the dimension, a spin of this exchange guy, and L prime is some extra sum.
Indeed. L
and
prime.
then so then you want this equation to be true for every L prime.
Yes. For every n and L. So
for every n and L prime, why can't you expect sum to go away only after summing to go away?
So in general, these L primes, the n and L primes are two independent numbers, which two independent numbers different from the spin and delta, as you can easily understand. And for each n and L prime, there is a conformal block in this sum, and they are independent of each other. So, since these things are all independent for each n and L prime, each coefficient of this block should individually go to 0, right?
So independent means there's some assumption about some independence and completeness and things like that.
Yeah, sure. But the thing is, you can simply decompose. So there's a Z and Z bar dependence in these blocks, and you can just expand these conformal blocks in the Z and Z bar, and each of these will give you a different initial power of Z and Z bar.
Right.
And you can just equate each of those powers individually to 0. So yeah, so there are always, yeah.
Okay.
Right. So yeah, so the question was, can we establish Polyakov bootstrap from usual crossing symmetry? So if there are no other questions, let me give you a quick introduction to a nice proof of Polyakov bootstrap that came out in a paper last year, and you might have heard some talks on this thing by one of these people. So the Polyakov bootstrap has recently been established in Mellin space in terms of the Mellin transform of a 4-point function. So the Milling transform of a 4-point function has the following form. It so it has some certain gamma function measure and a Milling amplitude, and you can just work in terms of the Milling amplitude of a CFT correlation function to understand the CFT correlation function itself. This Milling amplitude allows a very nice expression as a dispersion relation. So a nice a dispersion relation. By dispersion relation, I mean the following: that if you know about some of how the Milling amplitude behaves close to its singularities, you can retrieve the full Milling amplitude from that. And the dispersion relation that I am talking about has a nice feature. It's a crossing symmetric dispersion relation. It's a manifestly crossing symmetric dispersion relation, which is apparent. And so let me just show you that in this expression, in the integrand, what appears as a function cap big A is what I call a discontinuity. And the discontinuity of a Milling amplitude is nothing but a sum over residues across its poles. And then there is a crossing symmetric kernel. And this dispersion, and typically when you write a dispersion relation in for a quantum field theory scattering amplitude or even Milling amplitudes, you write the dispersion relation in terms as an integral over a variable s, but the variable t being fixed. But this is a bit different. This dispersion relation, for this expression, I have introduced a new variable which I call a small a, which is once again a crossing symmetry variable, and I have kept this variable fixed in this expression. So this is where the magic happens. So the dispersion relation assumes constant a, and the other thing that I assume to write this relation is a Regge behavior, which says that the Milling amplitude falls off slower than a square when you take the Milling variable s large but keep t fixed. And the singularities and then you get singularities from the integrand. So there are two kinds of singularities. One are the poles. So these poles are expected because a Milling amplitude for a CFT correlation function should have poles at the location of the operator spectrum. And then there are non-local terms, which are some weird terms which are inverse powers of this kind of expressions that follows from the dispersion relation. And these things come from introducing this weird variable a. And typically these kind of powers are not expected in a Milling amplitude. And if you set these powers to 0 by hand, the expression for this integral essentially reduces to a sum for Witten diagrams again. Milling amplitudes of Witten diagrams. So this is a compact in telling you the proof of the equivalence of Milling amplitude and Witten of a correlation function of CFT and sum over Witten diagrams in short. So the dispersion relation is also to tell you a bit more about these things. It also can describe a QFT scattering amplitude if you replace the Milling variables with the Milestone variables. And the bootstrap condition and, well, the Polyakov bootstrap conditions that I showed you before corresponds to the fact that you expect the only poles that you expect from the Milling transform is from the poles of the Milling amplitude and nothing else. So you should set all the residues of the gamma function measure to 0. And it has been shown. It has been shown in the first paper that came out that these conditions are exactly equivalent to other dispersion, CFT dispersion relations and dispersive sum rules that are present in the literature that you might be interested.
Just one question: that this G, Z, Z bar,
Yes.
this is calculating, and is it a prescription that you have to take all those poles to 0, all those residues, other residues to 0?
It's a prescription, yeah. So it's a prescription because it's a prescription, but it has to be, because a Mellin amplitude does not, should not have this kind of singularities.
Yes.
The only singularities in a Mellin amplitude, an atypical Mellin amplitude, are simple poles. So anything that are not simple poles should be set to 0, and that is what reduces them to some Witten diagrams.
So Apratim, is the spirit of this argument that you write down an expression that is manifestly crossing invariant and then demand that it have the right OP kind of singularities? Is that effectively incorrect OP kind of things?
Yeah. So typically, for any CFT dispersion relation, be it in Mellin space or position space, they are. So let's talk about typical Mellin space dispersion relation, which is not this, but what other people have done at fixed T. Here I've just the thing is I chose this new this new variable A, which is fixed, which was crossing symmetry, and in order to have this guy fixed, I came up with this weird kernel.
This way of functioning ensures that your MST will be crossing invariant. Is this right?
Yeah. Exactly.
Crossing symmetry on the object, and then you're demanding that it have singularities consistent with the OP. Is this right?
The singularities are consistent with the OP, indeed. So essentially, So if I have straightened super short, I gave up locality and I made it crossing symmetry. So this is one way to put it, if this makes sense.
Right. So these additional non-local singularities, whatever the additional singularities would be inconsistent with the OP.
That's right. Yeah.
Okay,
Indeed. So typically those singularities are not present in other approaches, but then crossing symmetry no longer becomes manifest. So at this point, let me. Sorry, is that question?
You demanded that you let go to start with, let go the local poles, local singularities or locality thing.
Yeah.
But then you impose crossing symmetry as well as also impose the locality condition later on, or you don't impose the locality condition? Sorry, I missed that.
I imposed locality conditions. I didn't impose crossing symmetry because crossing symmetry is already manifest. But locality condition is imposed through setting these guys to 0, these extra singularities, which I introduced because of my weird method. And so these guys need to be set to 0 by hand. So there are two, so to summarize, there are two independent kind of singularities which I should set to 0. One is these non-local terms, which make this whole thing equivalent to Witten diagram things. And then there are these Polyakov conditions, which I impose once again. So these things are different. These things are saying that, okay, now let's set to 0 the residues of the gamma function measure.
Right. So very, very naive question. If you suppose don't demand this locality thing, would you get something interesting, or that's something interesting or not?
That happens for, so that's a nice question, because that's hasn't been done for conformal field theories at least. And it could be that if these things remain, it could represent some non-local CFT. But I am not I cannot say for sure. So don't take my word for it. But when you are considering quantum field theories, so an effect quantum field theory scattering amplitude, which has the same dispersion relation, but you replace Mellin variables with Mellin variables, it's precisely these equations which are really give you the nice constraints. So for a quantum, for a EFT scattering amplitude, there is no Polyakov condition, but there are these locality conditions. So, and these things give you nice constraints over on parameters of your EFT, like vertices, interaction vertices, and so on.
Okay. Thank you.
So now let me focus. So all this discussion in this the discussion so far, I kept the dimension general. So now let me focus on one dimension. So the reason is in one dimension things are simple. It's just that. Whereas in one dimension the connection to position space of all these things is more explicit. Also, there are the positivity conditions of the bootstrap equations are more immediate. So these things, what I mean by positivity conditions will be apparent in a few slides. But these are typically important questions for bootstrappers. And also another reason is, well, if you have to generalize to bootstrapping different correlators, not just identical scalars, 1D is a nice place to begin with. So now let me ask, so I told you that Polyakov bootstrap conditions satisfy the optimal solutions to bootstrap, but I didn't explain really how. So now let me go back to the question, how does 1D Polyakov bootstrap find the optimal solution? Let us try to address the question in a bit more detail. So consider the Gaussian symmetry equation once again, the bootstrap sum over bootstrap vectors, 0. And so remember, if I haven't shown this explicitly, in the bootstrap vector, there is a S channel block and subtracted, and then there is a T channel block, which is just given by the 1 minus Z. So now, what I give to you, what I pull out of the hat right now is a new basis of the bootstrap vectors. And the new basis looks like the following. Previously, the basis that I gave to you was a simple Taylor expansion, a basis of derivatives. But now I'm saying that, okay, there exists a new basis of bootstrap vectors for the bootstrap vectors. And this basis looks like the following. It's that every bootstrap vector can be expanded as a sum over a bootstrap vector, which with the conformal dimension of 2 delta phi plus 2n, a double trace dimension, and a derivative of the same thing. So yeah, so this basis, it's like magic. I just showed. So yeah, it's not intuitive right now why it should be there. But if such a basis exists, there should be some functionals which should extract the coefficient of each of these basis vector, right? So if these two are independent basis vectors, then there should be two such functionals, alpha n and beta n. And these two I will collectively call omega. And the idea is that such functionals that if they act on the bootstrap vector, omega should peek out each of these coefficients. So there should be two types of functionals, alphas and betas, labeled by n, and each functional should act, if they act on this, if the alphas act on this, they would peek out the an, and if the betas act on this, they would peek out the bn. Please, I apologize for the notations, which may not be ideal, but, and in what follows, if there is any confusion about the notation, please don't hesitate to stop me.
Apratim, these functionals are then explicitly known, meaning the an function of delta.
They are explicitly known, yeah, and I will give a little brief introduction to how you can complete it. Anyway, I'll show this in a moment. So now to give you an idea of why this weird basis had to exist. So consider AdS2 and free theory. So, and as I told you before, a free theory in AdS2 has a conformal block decomposition, which look like the following. It's sum over conformal blocks of double trace dimensions with some OP coefficient. These OP coefficients are the GFF OP coefficients. And this is essentially the full expression for a 4-point of free scalar 4-point function. Now imagine that this was free AdS2. There was without any interaction. Now let's introduce interactions. So let there be cubic interactions and let there be quartic interactions. And if you introduce these things, then the corrections to such Witten diagrams, which is the correction to empty AdS, would look like the following, right? It should have exchange diagrams due to the cubic vertices, and it should have quartic interactions. Now, these guys should correct this correlator, which means that this guy, what can these corrections look like? These corrections can essentially correct the OP coefficient. These corrections can correct the conformal dimensions, and these corrections can at most introduce new dimensions to the existing correlator. And essentially all these things can be represented. So what all these interactions should look like is the following: is you can have a new dimension, new operator, or you can have corrections to the OP coefficient, or you can have corrections to the conformal dimensions. So these corrections must have this kind of a form. But notice that this interaction separately is a crossing symmetric solution to bootstrap itself. This is a quote unquote a CFT, a crossing symmetry. This is manifest crossing symmetry because, as you can see, it's obvious from the way I drew it. And if this crossing symmetric sum has to have this kind of a decomposition, this should satisfy the bootstrap equation, right? The basis that I told you about before is nothing but the bootstrap equation for the exchange Witten diagrams. So this line is nothing but this line equated with 1 minus z of itself. So this is why this basis should exist. So now let me tell you what these functionals, how these functionals should look like. So if these functionals need to pick out, these coefficients individually, they should, and if I plot the behavior of this function as a function of delta, it should have this kind of an expression, this kind of a plot. Why? It should have double zeros. So notice that if you have double zeros, then for example, take this alpha 3 guy. It has double zeros at all these places, all these double trace operator values, except the double trace value at this point. So what this means is that if it acts on the bootstrap vector, it will pick out A3, right? And for the betas, it's similar. So it should also have double zeros, but at some point it should have a simple zero, because then in that case, the derivative of the solution should be non-vanishing, so that beta picks out this coefficient. So the derivative of this plot should be non-vanishing at this point.
Sorry, Apratim, I didn't quite understand this double zeros. Could you say it again? I mean, why should alpha have double zeros like that?
Alphas should, so let's take a look at, let's say, take n equal to 3, the example that I took. So alpha 3 should act on this whole thing. And if alpha 3 has to pick out A3, then it should set to 0 all of these things, which is not A3, not n equal to 3, right? And it should also set to 0 all of these things.
Derivatives.
It should only be non-zero at n equal to 3.
So acting on these derivatives means setting the first derivative 0 at alpha.
Yeah.
By partial integration or something. No.
So say it again.
just wanted to see it clearly, that action of alpha on del delta.
Yeah, it means so you can, so if the alpha acts on this thing, you can essentially, why is derivative, why do I care about derivative of alpha with respect to delta?
Yeah.
It's because if alpha acts on this thing, so alpha will essentially go through this derivative. You can commute the action of this derivative and the action of alpha. So it means the action of yeah. So I commuted the action, this guy with the action of alpha. And this plot is also kind of already tells you how this optimization happens. Because if you look at this, for instance, yeah, if you look at this, for instance, if optimization happens, because if you say that, okay, so if you have some operator here, and so that is the gap, then there are very few ways you can solve the bootstrap equation. And if if your gap appears here, automatically the positivity of this plot tells you that there is no solution possible at all. So this is how one solves the maximization of gap numerical problem. And this is the so Abhijit asked a while ago that how do you solve for these guys? So the structure of the functionals have the following form. They are basically an integral, and the integral has some kernel of integration, and it acts on the conformal block. It acts on the bootstrap vector, the imaginary part of the bootstrap vector.
Sorry, Apratim, one more question. So just the way you define these alpha functionals, not this, but previously the way you were talking about the coefficient, from that expression, is it clear that these are linear functionals?
You mean from this expression or the one that
No, I mean the previous expression.
This one?
Yeah, no, I mean that exactly.
So I assume that it's linear, right? I want it to be linear. So yeah, it has to be linear to work. Yeah, it's linear functional. I mean, it's not clear because now I haven't really showed you what these functionals are, but for it to work, it has to be
no, I mean, just the way they are defined from there, is it clear that they are linear, or you have to work harder to see that?
So omega acting on this thing is equal to omega acting on these guys, all of these guys separately, and essentially depending on what omega is, you get one of this coefficient. I mean, this definition is not telling you much, but I already assume that omega is linear in this definition. It's not really a definition of omega, but yeah, I'm not sure if this is
basically why does this analysis itself not give you these functionals? Why do you have to write an integral form for that? Because you can, it's just a matter of now finding the function an of delta, right?
Yeah, but sure, but
one doesn't know the expansion in terms of these Witten diagrams, in terms of these arbitrary operators. Is that the point?
It's not really. So the thing is, the alt-text, whatever is the expression for the functional, it cannot depend on delta beforehand. It cannot know about delta. It has to be, it can at most depend on phi, delta phi, but it cannot, so it has to act on this thing to become a function of delta.
Yeah.
Right? So, I mean, so the thing that I showed you is a function of this guy are functions of delta. So this is not really any functional. So functional has to be like an integral.
Yeah, that's what I was asking. But you argued that it is linear. I mean, the way you defined it.
Indeed.
I just don't see the insufficiency of this approach. But okay, go ahead.
So if you're asking what, so if your question is, do I really need to care about an explicit form of the functional integral? Is that what your question is?
Yeah, if I know these functions, I know that those come out as a linear action of a linear functional. Then I'm happy with this
but
n of deltas, alpha n of deltas as functionals, right?
Yeah, but you still don't know what this a. You just know the roughly the behavior that they should look like the following, but you don't know exactly how they should be. I mean, what are these ANs and BNs? So we don't know beforehand.
Okay.
I just told you, yes, they has to have roughly this kind of shape.
I see. Okay. Yeah.
So the function of the structure of the functions should have this form, and so I say they take the form of an integral, and this integral is over this point. So in the z plane, the integral is runs along this part of the contour, and with some contour manipulations, you can bring this form in a form of two integrals where these g's and f's are related to this h. So don't look into too details of this whole slide, because they are not really important. The only reason why I'm showing you these details is that to convince you that there is a nice systematic way to come up with, to construct this integral. So they can be constructed, and they can be done with certain contour manipulations. And with this, you can bring part of the integral. So this, you can divide the integral into two parts. One that lies along this, one that lies along here, and the other that lies along this part. And this and the magic happens because, and then the nice thing that happens is that the part that is here, the part that is here gives rise to a cos function, and that happens because a cos of pi times this thing. And so that's essentially that this thing gives this oscillatory behavior that I was expecting. So now the thing that you need to do is put conditions on what these g's and f's are, which look like the following, and try to find what these f's and g's can be. So these f's and g's just need to be related to h in a certain way, and they also need to be such that you reproduce this cos an oscillatory function. And one way to do this is that the f's and g's can be some 3f2 hypergeometric function. So there exists a solution to these kernels. So this was the most mathematically very complicated part of this whole talk. The other extra conditions that one should impose are orthogonality.
Yeah, Apratim, I think I'm getting maybe I'm mixing things up.
Yeah.
So the functional here is the one that kills these is defined by something. So can you go back to the previous slide? Yeah, I'm just not this one.
No, sorry.
Yeah, so if you look at this corner equation, f delta is equal to this. So what is the functional? The functional is some action which is annihilating these f delta phi plus 2n and their derivatives and such, right? And the point is that whether such a thing exists or not is not clear. Is that the point? How do you know that such a functional exists? Or
how do I don't know. So maybe I didn't understand the question. So I just wanted this oscillatory behavior, but that was clear already to you. But then now, what do you are worried about? That
no, I mean, if you assume that there is a functional which does all these things that you want, namely it vanishes on f2 delta phi plus n for n not equal to something,
yes,
and also it vanishes on the derivatives, then it should take this form is clear. But
yeah.
But whether this functional exists, a function of this type exists or not, is it a priori clear why it should exist?
No, is it a priori not really? Not
only after this construction on the next page does this become clear. Is that the case?
That is true. Well, it would be really surprising if that.
But I remember my friends had something like that. That they just from this fact they were able to plot these things and such.
So I'm not sure. So the thing is, so for me, for this one, the case that I'm talking about, so it's not the only reason why this should happen is that it is quite clear that the basis of the bootstrap vectors exists. This I'm 100% sure of. And if there exists such a basis, then there should be function. It's like Taylor expansion, or it's like Fourier expansion, whatever you want. It's like Fourier transfer. So if such a basis exists, there should be a functional that should pick out this.
I see. So you are saying just from this equation, f delta of z is equal to this, then there should be exist some functionals that have this property.
Yeah. If
okay. And why is this equation true in the first? I mean, not true, but expected in the first place. This f delta is equal to sum over. I mean that one should be able to take this bootstrap vector and decompose it like so.
Why should you exist? Why should such a
thing
exist?
Could you remind me, because
Sorry, I just have to go back. It should exist because so in AdS 2 you can write a crossing symmetric combination of Witten diagrams that decomposes into double trace operators and the derivatives. So this basis I told you is nothing but the bootstrap equation for this decomposition. So this equated to the same thing with 1 minus z. So it's
I see. So sorry, what this is crossing symmetric. So you just take this and minus 1 minus z kind of thing, and then you have on one side that and the other side this.
Exactly. Yeah.
No, but this right hand side will also have 1 minus z, right? Not z.
So maybe I can write this thing if you want.
Right.
So so if you have something like g of delta plus sum over an g of delta n plus b of n derivatives of g of delta n. I'm saying that, and all it says, this guy should be equal to g of delta 1 minus z plus sum over an g of delta n 1 minus z plus bn.
Okay.
1 minus z. So now you can write g of delta of z minus g of delta 1 minus z equal to sum over an's g of delta n 1 minus z minus g of delta n.
That there we also had f's, not g delta. I see.
Yeah.
So this is your f, I say. Okay.
So it does derivatives. So let me just, for the sake of completeness.
No, got it. Yeah. I thought there you just said g delta.
Right.
I see f on both sides. Yeah. Yeah, sir. Yes. Thank you.
Yeah, thank you. Yeah, no worries. So is there any other question?
Yeah. What is surprising is that, thinking about perturbative Witten diagrams is giving you some functional, which is kind of useful non-perturbatively.
Right.
This was a bit surprising thing.
It is that is correct. So I'm just using it to establish a very concrete basis. And the only purpose of that is indeed just a concrete basis for generic bootstrap equation. By the way, to answer your question, there is a reason why actually. So you're worried about why if it automatically implies that a functional should exist, and it's a good question because it would. So it would be possible that such functional does not exist if this basis was over constrained. If there are too many complete, if there are too many bootstrap vectors, if there are too many basis vectors, more than the what I need. So if that happened, then certainly I wouldn't be able to find a certain nice function.
Right.
But thing is, the fact I can essentially means that.
But as you said, right? I mean, you can just expand in powers and use the first. You can pick out the first guy by just looking at the top power, the lowest power, and then subtract it off, like look at the second guy. So that way you can do the ANs, and then I guess the B term would have log Zs. So that you can do it separately.
That is indeed true.
So in that sense, you can pick out all these coefficients.
Exactly, sure.
Okay.
So, so that is indeed. That's one argument.
Okay, thank you. Sorry for slowing you down.
No worries. Thanks for the question. And so please stop me if you have other questions. So there are some extra conditions that you need to impose on the kernel. And these extra conditions say that, okay, the action of the functionals should be orthogonal on the basis vectors. And they should also respect the Regge boundedness in the U channel, which is equivalent to imposing the usual Regge boundedness on the median amplitude. And so the Regge boundedness in the U channel has the following form. And if the kernel should satisfy both these properties. So with that, essentially the structure of the functional, constructing the functionals is complete. The equations that you get from the functionals are nothing but the action of the omegas, alphas and betas on the bootstrap equation. And you get, and since there are two functionals, alphas and betas, you get two sets of equations. And these equations look like the following, and they're essentially the same as the Polyakov bootstrap conditions. So summarizing everything that I've said so far, I discussed the optimal bootstrap bounds, which correspond to some interesting CFTs. I showed you why the generalized free theory can be trivialized through a change of basis in the conformal block expansion. I introduced a new basis for the conformal block expansion. And I showed you that this corresponds to a set of new kinds of functionals, which are called analytic functionals. And the bootstrap equation could be transformed into a form where in terms of the Witten diagram coefficients. So just to, since I didn't say it very clearly, these equations, these guys are all coefficients of Witten diagrams. So the whole song and dance that I have done, that I talked about, they were all to essentially to have. They were in the end, they are not really necessary. In the end, everything can be replaced as Witten diagram coefficients. So the functional bootstrap is essentially the same as Polyakov bootstrap. So now this has been established. All right. So now let me move on to some more complicated problems, which is so in order to obtain tight and more constrained bounds on conformal bootstrap from bootstrap, one should not focus on only bootstrapping 4-point functions of scalars. One should identical scalars. One should also include other correlators, like ones with non-identical scalars, and so on, or more than one scalars. But how can we do that? So can we extend dynatic functional ideas for multiple correlators? But a more basic question would be that, can we do the same thing? Can we at least have the same ideas? Can we at least generalize the same ideas for n's for multiple scalars that are related by a global symmetry? So any problem, so before we move on to multiple correlator problem, let me tell you this fact that whenever you're bootstrapping more than one scalar, usually the problem looks like the following. You have a set of functions which are dependent on z's that are related to the same things, but at 1 minus z through some matrix. And usually you have to diagonalize this set of matrix equations. And this diagonalization procedure gives you a set of crossing symmetry equations and a set of crossing anti-symmetry equations. So before we move on to dealing with correlation functions of more than one scalar, it is necessary to at least spend some time on crossing antisymmetric equations. The crossing antisymmetric equation, what is that? It is essentially, it looks like the following. And let me ask, can we have analytic functionals for these guys as well? So, and indeed, it is possible to have analytic functionals for these things. So in 1D, the crossing antisymmetry equation also decomposes into bootstrap vectors, and these are given by G delta Z plus of G delta 1 minus X. And the nice thing is there does exist analytic functionals for this thing, because there it can also write bootstrap a basis expansion for these F pluses. These F pluses are similar to the other bootstrap vectors, but with a plus sign. And the basis expansion for these guys look like the following. They are evaluated at 2 delta factors 2n plus 1s. And in fact, the functionals have a similar form. I call them omega plus functionals. And now you can ask, can there be a Polyakov block for this kind of function? Can there be a Witten diagram description for these guys as well? And indeed there is. The Witten diagrams that give you the plus type functionals that are basically scalar Witten diagrams with a spin 1 exchange in AdS2. But they have to be arranged in a crossing antisymmetric way. So for instead of having a crossing symmetric combination of Witten diagrams, I now arrange Witten diagrams in a crossing antisymmetric way with the minus signs. This is a totally antisymmetric. This has manifest antisymmetry, and it decomposes into exactly the blocks that I needed. And so since L is odd, and since this guy decomposes into odd spin blocks, and I also needed odd double trace operators, this exactly does the job for me. So in fact, one can also show that this description in terms of Witten diagrams also follows from a dispersion relation. It in generic dimension, it establishes the same thing for you. And yeah, I'll just skip over this quickly because it's very similar to the crossing symmetric case. So the crossing symmetric functionals, just review the what I just told you about. So they are very useful because in higher D, in even D, you can conformal blocks can be written as sum over products of 1D blocks, and they can be rearranged into antisymmetric and symmetric bootstrap vectors. So from plus and minus type functionals, you can reconstruct functionals for general dimension. Also, if there is for crossing symmetric problems involving fermions, these functionals can become important. But my original motivation was correlators of more than one scalar. So that's what I will be talking about now. So yeah, and this is almost the last part of my last few slides of my talk. Before I go there, is there any question? I hope I'm not losing people. So yeah. Okay, so the final problem that I want to tell you about is the problem of robust symmetries. And well, so let me consider a 4-point function of ON scalars with an ON in, let's say, global symmetry index I. And yeah, and the crossing symmetry problem that I would like to discuss is for a function of this kind that carries IJKL indices. And yeah, so in this problem, the OPE of phi I and phi j has the following irreps: the singlets, differential symmetric and asymmetric, which you know very well, and the decomposition And the 4-point function decomposes into these ON sectors: singlet, symmetric, and antisymmetric, which is kind of expected. And as I told you before, the crossing symmetry equation looks like the following. It's given by, so for each of this GS, GT, and GA represents the sector of the correlation function in terms of for the S, T, and A sectors, and it's related to its crossing components via crossing matrix, a matrix. And if you diagonalize this equation, you need to diagonalize that equation, and the crossing matrix happens to have eigenvalues plus ones and minus ones, and eigenvectors of these things, eigenvectors of the one eigenvalues dotted with the vector GS, GT, and GA gives you a crossing symmetric component of the correlation function, and the one with minus eigenvector gives you a crossing antisymmetric component. So essentially, from the one crossing symmetry equation, matrix equations, I get a set of equations, two of which are crossing symmetric and one of them is crossing antisymmetric. And now you can easily use the technology I discussed before. You can see that these guys are crossing symmetry equation, so you can easily use the 1D functionals, crossing symmetry ones, to expand each of these two equations, and then use the crossing antisymmetry functionals to expand this guy. There also exists so this way of expansion it essentially means that I am using a basis for double trace-like operators for all the singlets and traces symmetric and antisymmetric guys. There also exists another different basis where you can be a bit more careful, and you can instead, this basis is called the ON-GFF basis, the generalized free field basis, and where you can expand this guy, where you can expand these guys around traceless symmetric vector and singlet vectors at these values, and the antisymmetric guys around these values. So this clever way of doing it is called the ON-GFF basis, and there are two types of basis for this global symmetry functions. So yeah, this is kind of close. So so let me just summarize the story of global symmetry functionals. So constructed for you so yeah, first of all, I should talk to you about crossing antisymmetric functionals which exist and related to odd spin-Witten diagrams. And then I showed that that for bootstrapping global symmetries, it depends. You have to include both. It divides into crossing symmetric equations and crossing antisymmetric equations, and you can have functionals, two types of functionals for deal with this kind of matrix equations, and essentially there is a simple functional basis which just straightforwardly uses the 1D crossing symmetric and antisymmetric functional basis, and there also exists a GFF functional basis that corresponds to using a basis that diagonalizes that corresponds to the ON GFF. So this whole story can also be generalized to any global symmetry. So any questions so far? And otherwise I will just move on to showing some applications of these ideas. So one of the applications that results that I would like to tell you about is the one on the 3D Ising twist defect. So the 3D Ising twist defect is defined as in the following way. Suppose you have the Ising model defined on a lattice, and you consider a semi-infinite plane on which you reverse the Ising coupling J. So for all points that is not on this plane has positive J, for instance, and the points on this guy on the plane itself has negative values of J. And the boundary of this semi-infinite plane is what is called the 3D Ising, the twist defect. And this line is a 1D CFT, the one. And what happens on this defect is the following: is that in the bulk theory at the fixed point in the bulk theory, I had the SO4 conformal group, and the introduction of this and this plane breaks the symmetry into 1, 2 1D conformal group and a O2 global symmetry. So now you have essentially a 1D CFT with a global symmetry. And there also exists some other symmetries on this 1D line, which is called the S parity, resulting from the x going to minus x symmetry. And there also exists the Z2 symmetry that was in the bulk. So the bootstrap problem that I will discuss in super short is the one for a 4-point function of spin half operators, which are spin half under this O2, and a few of this and in this decomposition, some of the dimensions of the few of the operators are actually known from numerical simulations. For instance, the one that are known is the dimension of delta phi roughly, which is around close to this, the dimension of the first singlet guy, and then the dimension of the what is called the displacement operator, which is actually exactly 2, a property of the twist defect. And the problem that we looked at is maximizing the dimension of the first singlet dimension, maximizing the first singlet operator by varying the OP coefficient A of AD of the displacement. And yeah, and we got some nice results. So and some of these results were computed before, but we were able to improve upon them, and the results before included. So, for example, the results before included the numerical bootstrap with derivatives, but you see that we have with the analytic functional method, you don't need really, you can already go to more precise results introducing just 2 or 6 functionals.
Yeah, how does this happen, Apratim? I mean, why are they inherently better, these analytic functionals? For this, I mean, for problems which are kind of close to generalized free fields, I can understand, because these functionals are made from generalized free fields, right? Yeah. But for a non-perturbative problem, it seems a little. I mean, why are these so effective for non-perturbative problems?
So you can, in principle, imagine even this CFT as a perturbation theory around GFF, but with a slightly bigger perturbation, with a finite perturbation theory, but it's still quite close to GFF. So if you, so in this way, so it's, but there is nothing for the derivative problem. I mean, GFF is as far away from the derivative in the derivative approach as 3D Ising twist defect. So it doesn't really help. So that it's not GFF. But since GFF is all, so the 3D Ising twist defect is essentially close to GFF. You can imagine that way. So 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 that's how it becomes simpler.
Okay.
Already. The other problem that we looked on is kind of a new is an interesting idea, which is the problem of bounding correlation functions. And so in this problem, what we want to do is not find the operator spectrum themselves, but trying to find bounds on the whole correlation function. And the idea is this, that let us parameterize the one correlator as a vector, where the first component is GS, GT, and then GA. And then we pick a certain direction in that tells a certain direction along which this vector can lie. You fix this direction and you ask what is the maximum value of the mode of this vector that is possible. This thing is also a linear problem, just like usual bootstrap problems. So in this, what we now want to, the problem is, can we maximize or minimize the amplitude of this vector, the one vector, the correlation function vector, so that the sum over the conformal blocks is equal to this, and well, it also should satisfy the bootstrap equation. And then there are two things that we need to input for each, a direction, a unit vector, and also some value of z. So because we want to maximize the correlator for each value of z. So we can take, for instance, z equal to half, or z equal to something that is not half. And for z equal to half, the three sectors, singlet versus symmetric and asymmetric, they are actually not independent, because, well, z equal to half is a cross-symmetric point. So there is no antisymmetric combination of the bootstrap vectors. So since the antisymmetric sector of the correlation function is 0, it sort of relates the three sectors. And the other point, which is for other point, they are actually not independent, and you get a more non-trivial plot. So yeah, so these are the two plots that we obtained, one for z equal to half and the other one for z equal to 1/3. So yeah, so one of them is a 2D plot because the direction GA is not independent, and yeah, and here all these directions are independent. So these pictures denote the maximum and the minimum values of the correlation functions at these points.
And also at the corners, you find something that is known.
At the corners for this problem, the things that are known were for example, at this point, these are some weird CFTs. These are related. So at these points, so recall that my axes are the tracer symmetry sector and the singlet sectors. So this point is actually the point where GT is a fermionic GFF, and the singlet sector is also a fermionic. So the opposite. The singlet sector is a fermionic GFF, and the T sector is also fermionic GFF. And this actually is a valid CFT. So it's a very weird CFT because it's not really the usual generalized free field theory. But it's
valid meaning it obeys crossing. It obeys the crossing equations that we have looked at.
Yeah. Okay. And it is weird.
I mean, there is no independent construction of the CFT.
There's no independent
swampland.
No.
Okay.
Yeah, sure. But the thing is, and for me, it was weird because it has, for instance, it has an identity operator in the traced symmetric sector, but that is usually, these things are not present. So yeah.
No, because I was wondering if you kind of find this this then looks like an optimal set, which is what was surprising.
Indeed, it is that is exactly true. Indeed, these kind of CFTs are optimal solutions for the ON problem. And yeah, so the GFS solutions are actually not the optimal solutions. So that's a bit surprising. So yeah, the optimal solutions in these cases are not the usual GFF, but it's weird GFF solutions. So to summarize, this is the last slide. The analytic functionals are dual to a basis that trivializes the generalized free field theory. The analytic functionals for crossing symmetry and asymmetry are described by Witten diagrams that these things make the approach easier to deal with. The global symmetry problems, bootstrap is formulated in terms of a crossing matrix, and using 1D functional ideas, one can get the simple functionals or a global symmetry functionals for the global symmetry problem. And then I described two numerical applications. One was for the Z2 Ising to its defect spectrum, constraining the Z2 Ising to its defect spectrum. Another numerical application was bounding scalar the whole correlator itself in a one theory. So yeah, so that's the end of my talk.
Let's thank Apratim for
So
the
I
nice
just
talk.
leave.
Yes.
Let's leave with this slide for future directions.
Are there any questions? Great. If not, maybe let's thank the speaker again.
Thank you, Apratim.